In section 21, we will continue examining the graphs of polynomial functions. The behavior of a function is a series of intervals of increasing and decreasing. Two examples are shown below. Now, when we're examining the behavior, we're going to work from the left side to the right side, and we're going to decide if we're going up or down. In other words, increasing or decreasing. So if I were to start over here and I'm tracing this graph, I am going to go up until I get to this high point in the graph, and that means I'm increasing in that region. Then I'm going down in this region, so that's decreasing, and then I'm going up. And then there's no more behaviors after that. So therefore, that was increasing, decreasing, increasing. And you can either write like the abbreviation of this, INC, or you could just draw arrows showing that it's going up, then down, then up. Over here, again, if we start on the far left and I trace this, it's going down, so decreasing, then it's going up, so increasing, it's decreasing again, and then it's going up, so increasing at the end. So decreasing, increasing, decreasing, increasing. Now the point where the function changes from increasing to decreasing is called a relative maximum. So in other words, it's a high point in the graph. So when we go from up to down, that gives us a high point in the graph. And that is an example of a relative maximum. In this graph, again, if I'm going up and then switching to down, it's considered a high point in the graph. And it's called a relative maximum because it's not the actual highest point, the maximum point in our graph. You can see that in both of these situations, I do have points that are going to be higher than that within the graph, but it's called a relative maximum. Then our relative minimum are the low points of our graph. And that's going to be where we're changing from decreasing to increasing. So when we go down and then back up, that's when we have a relative minimum. And that's going to occur right here in this graph. And in this graph, there's actually two because, again, it goes down and then up. So that's one. And then over here, it goes down and then up. So that's the other one. Now we're going to take a look at some graph examples and state the behavior of them, and then determine how many maximum, minimums, and finally the degree of the polynomial. So for this first one, when I'm looking at the behavior, this is going down and then it's going up. So it's decreasing and then increasing. As far as the relative maximums, I don't have a high point in this graph where it's changing from increasing to decreasing. Therefore, I don't have any relative maximums. Then for my relative minima, I've got a point down here where it's going from decreasing to increasing. And so therefore, I do have one relative minima. The degree of this polynomial, if I examine how many times it crosses the x-axis, I can see that it crosses twice. Therefore, my degree of this one is going to be 2. And we kind of want to look at some patterns that are going to start to form as I'm going through these different examples. Number 2, again, if I'm looking at the behavior here, starting here, it is increasing, then it's decreasing. Relative maxima, I have a high point right here where it changes from up to down. So I have one of those. For relative minimums, I'm not going to have any. And then as far as the degree, again, it's going to cross twice here, making the degree of the polynomial 2. And again, I want you to look for a pattern that's going to start to develop within those answers. Here, when I'm looking at the behavior, again, I'm starting here. I'm going to go up, then down, then up. So I had 3 behaviors here. Relative maxima, a high point would occur right here. So that's 1. A low point occurs right here, so that's 1 for the minimum. And then the degree of this polynomial, again, if I look at the number of real zeros here, I've got 1, 2, 3, and that's going to be the degree. For our next one, behavior, it's going to start here. It goes down, then up, then down. So again, I'm getting 3 behaviors there, decreasing, increasing, decreasing. Maximum is going to occur right here, so there is 1 of those. Minimum occurs right here, so there's 1 of those. And then as far as the degree of the polynomial, again, if I look at the x-intercepts there are 3 of them, so my degree is going to be 3. For this one, again, our behavior, I start here, and it's going down, and then up, down, and then up. So decreasing, increasing, decreasing, increasing. Relative maximum, the high point here would be this point right here. So I have one of them. For relative minimums, those are my low points, and I'm going to have two of those. And then finally, for the degree, if I'm looking at the number of x-intercepts here, I have 4. So the degree of the polynomial is 4. And again, we're looking for some patterns to be developing here. I have 4 behaviors, and it's a 4th degree. And if I looked at each of the previous examples here, I would see that same pattern, that the number of behaviors is going to match up with the degree. You also want to make a connection between the total number of max and minimums and then the degree of the polynomial. So you're noticing here I've got 3 and the degree is 4. So look for a pattern to develop with that. On this one, it's going to increase, then decrease, then increase, then decrease. So that's going to be our behavior. Maximum would be these high points here and here. So we have 2 of them. Minimum is this low point right here. So we have 1 of those. And then for the degree of the polynomial, it is going to intersect the x-axis 4 times. And again, we're looking at the fact that this matches up with this. Also, the total number of relative max and mins is 3. And again, our degree is 4. So we should be noticing that that is going to be 1 less than the degree here. So now we're going to kind of, based on those patterns that we're developing, we're going to answer some questions. So for number 7, how does the degree of each polynomial compare with the number of times it was increasing or decreasing? And again, we discussed that, and it's going to match. If the polynomial function has no complex 0, the degree is going to be the same amount as the number of behavior changes. For number 8, how does the degree of the polynomial compare with the combined number of relative max and mins? Well, for that, assuming it has no complex zeros, the degree is going to be equal to the total number of max and mins plus 1. So the degree is always 1 bigger than the total number of max and mins. So then for number 9, they're telling us that this is a 5th degree polynomial and that it doesn't have any double or complex zeros. How many total relative max and min? Well, again, if it's a degree of 5, the total of relative max and mins should be 1 less than that, so we should have 4. For number 10, this is a 6th degree polynomial function with no double zeros or complex zeros. If it starts with increasing, and we're going to write the behavior. So again, it's going to start by going up, and I have to write 6 arrows, and it's going to alternate. So it's going up, then down, then up, then down, then up, then down. For number 11, a quartic polynomial, so this is a 4th degree. No double, no complex, and we want to know how many total max and mins. And the total number of relative max and mins should be 1 less than that, so I should have 3. And now we want to look at the different graphs that we looked at today and notice the impact of double zeros, both on the behavior of the function and also on the number of relative max and minimums. And what we want to realize here is that they didn't actually have any impact at all. We still had decreasing and increasing at zeros, and they could be relative max or minimums. So they do not have any impact on the behavior of our graphs. Now, when we talk about end behavior, so far in this section, we've really only referred to the end behavior on the right side. So I can see that for this one, it's pointing up. If I put an arrow on that, it would point up forever. So it's going towards positive infinity on this side. This one over here is going down forever, so it's going negative infinity on this side. And then this one is going down forever on this side. Now, as we go to come up with the other side of this, you have to make sure you're thinking about where the arrow would be pointing. So we're not starting here and moving this way. We're actually starting here and thinking, what is it pointing to? And this is pointing down, so it's pointing towards negative infinity. So when I'm looking at that value right there, if I ask for the limit as x approaches negative infinity, that means as I go further and further into this region, what is going to happen to this section? And it is going to go towards negative infinity forever. And that's why we're going to put negative infinity there. The other side of that is going up forever. So that means it's approaching positive infinity on that side. Another thing we want to think about here is this is an odd degree polynomial. We know that because we have 3 real zeros on this one. So it's potentially a 3rd degree, technically could be a 5th degree if we had additional complex zeros in something like this. But again, we're expecting that these are going to be opposites of each other if we have an odd degree. On this one, when I go to write out these, my left side right here, it is going towards positive infinity. So on the left side, as x is approaching negative infinity, this being negative infinity on this side, we are going towards positive infinity. On the right side here, it's going down forever. So that side is going to approach negative infinity. And again, degree here could possibly be, it's definitely not a first degree. This is most likely going to be a third degree polynomial function. Again, odd. So again, pointing in opposite directions, and these being opposite. On this one, the limit on the left side, again, is pointing down if I were to put an arrow on that. So that's going to go towards negative infinity. And then same thing for the other one, it would go down. So this one is also going to be negative infinity. And for this, again, if we're thinking about what the degree is of this, the degree is going to be for sure even on this one. I see 1, this counts for 2, 3, 4 zeros that are kind of shown in this problem. So again, that's an even degree, so we're expecting that these are going to match. So do the same thing on these problems. Again, on the left side here, the negative infinity side, it is going up if I put an arrow on that. So that's approaching positive infinity. On the right side, it's also going up, it's approaching positive infinity. For the next one, if I'm looking at the left side again, it's going up forever, it's approaching positive infinity. Whereas on the right side, that one's going down forever, so that's approaching negative infinity. And then for my last one, on the left side, it is going towards negative infinity. On the right side, it's going towards positive infinity, so that would be our behavior, our end behavior. End behavior is determined by 2 factors. One is the sign of the lead coefficient, which we've been talking about throughout this unit. The other is based on the degree of the polynomial. So this is an example where the lead coefficient would be positive, and we know that because it ends on the right side, it's up. This is an example of a degree 2. We know it's going to be an even degree because they both point up at the start and the end of this. Now if I start to look at the behaviors of these, on number 1, the left side behavior is going to go to positive infinity. Again, what I'd be looking for here is that it extends up forever. The other one is also going to go towards positive infinity. Again, that was an even degree, so these should match. For number 2, when I look at the left side there, that would be pointing down forever, so that's going to go towards negative infinity. And again, I'm expecting these 2 to match. And on 3, left side is going down forever, so that's negative infinity. Right side is going to go up forever, so that's approaching positive infinity. Taking a look at these graphs, here I can see that there's 1, 2, 3 real zeros. I could also address that the behavior would go down, up, down. So again, 3 behaviors means a degree of 3. The leading coefficient here must be negative since it ends down. The left side behavior here is going to go towards positive infinity. The right side behavior here is going to go towards negative infinity. Again, that odd degree, we did get opposite directions here, opposite values here. In the next one, I'm looking at a degree of 4 because we have 1, 2, 3, 4 zeros here. I could also see that the behavior goes down, up, which is another reason for this to be a degree of 4. Lead coefficient here must be positive. So again, I'm expecting the same outcome for these because it is even. And then since the lead coefficient is positive, they must both be approaching positive infinity. And they are according to this graph. And then for number 6, this degree is going to be 4. We've got 1, 2, 3, 4 solutions. The lead coefficient here must be negative because it ends down. So now when I'm looking at these, I'm expecting them to be the same, and I'm expecting that both of them are going to be negative. So if you know the degree of the polynomial function along with the sign of its leading coefficient, how can you determine the end behavior of the function? Well, if your lead coefficient is positive, the right side, or the positive infinity side, is going to be positive infinity. If it's an even degree, you're expecting the same outcome for both. So they're both going to approach positive infinity. If it's a positive lead, again, we're expecting the right side, the one that's approaching positive infinity, to be a positive infinity. But if it's an odd degree, I'm expecting these to be different. They're opposites of each other. So this one's approaching negative infinity, this one's approaching positive infinity. If our lead coefficient is negative, I'm expecting that bottom one, or the right side, to be negative infinity. And then if it's even, they're going to match. So these are both going to approach negative infinity. And then over here, again, I'm expecting the bottom one to be the negative infinity, the one that's on the right side. But then the left side one is going to be the opposite of that. So that would be our answer here. So go ahead and fill in questions 7 through 12 and see what you come up with as far as the degree of each of these. Now in number 7, we see that it's got a negative lead coefficient. So that's going to tell me that the right side of this is going to be negative infinity. I also see that the degree is odd. Since it's an odd degree, I'm expecting that these are going to be opposites of each other. And they are. So I'm getting a negative infinity on the right, I'm getting a positive infinity on the left. For my next one, again, I'm going to look at the lead coefficient is negative. That's going to tell me the behavior on the right side. It's going to be negative infinity. Then I want to decide if these are going to be the same or opposite. Well, here the degree is going to be even because we'd have to the first power, so that's 1. That's 2 more, so I'm at 3. That's 1 more, so I'm at a 4th degree. And therefore this is even. So they're going to be the same, both negatives. In number 9 here, I've got a positive lead coefficient, which means it's going to be positive infinity here. From there, it's an odd degree, so I am going to get opposite answers for these two. For 10, this one is going to have a positive lead coefficient, which means the one on this side is going to be positive infinity. Then the degree here is going to be to the 2nd. This is going to make it to the 4th. 1 more, so it's a 5th degree. And that means it's odd, so I'm expecting them to be opposites of each other. In number 11, again, I've got negative in front, so it's going to approach negative infinity on the right side. And then it's an even degree here, so they're going to match, and they're both going to be negative infinity. And then for 12, I've got a positive lead, so I know that this one is going to be positive infinity. Then from there, this is to the 2nd, this is the 3rd, the 4th degree, which means it's even, so they're going to be the same. So please complete the exit slip for today, as well as practice that